Welcome everyone. We're going to be presenting a combined theoretical and experimental study of a very interesting question, which is what is the shape of a body that is dissolving or melting under natural convection? So we're generally motivated by the question of how buoyancy-driven flow sculpts bodies around us. And it turns out that the natural world is filled with examples of this. So one example is a melting iceberg. So an iceberg in a warm salty water will produce a narrow flow of meltwater along its underside, and the dynamics of that flow will control the rate of melting, and that will cause the shape to evolve. And so there's an interesting two-way coupling there between the buoyancy-driven flow and the evolution of shape. Another interesting example are the stone forests of Madagascar, which form these remarkable limestone structures. And what's thought, one theory for why these arise is that this region was once submerged in water, and these limestone spires have formed from dissolution into the water. And a nice everyday example of coupling between buoyancy-driven flow and melting is a melting ice cube, which we've got at the bottom here. And in this case, the ice cube creates a cool flow around the ice cube, which is denser, and that flows along the sides of the ice cube and along the top, and that will control the shape evolution in time. So to illustrate the kind of problem that we're interested in, this movie shows the evolution of a sphere of rock candy that's dissolving in water. And what you can see is that the underside and overside form characteristically different shapes. And so the lower surface is very rough, whereas the upper surface is smooth. And the underside has been considered by various authors, and the conclusion there is that the recession speed is controlled by the dynamics of unstable convection to produce a uniform and constant recession speed to good approximation. But what we're going to be talking about in this talk are the dynamics of the overside. So there are lots of interesting open questions to do with this problem. And one very basic question is, what is the shape that arises from the two-way coupling between shape change and buoyancy-driven dynamics? And you can see from this movie, which is of a dissolving cone of candy, that the tip is moving down at a certain speed. And so a very simple question is, how quickly does that tip move down? Another question is, if I zoom into the tip, is there a universal or fundamental tip shape that always arises near a dissolving or melting tip? And a related question is whether that tip shape sharpens or blunts with time. That's an interesting question. You might think that a dissolving process, for example, is always smoothing, but it turns out this is a non-trivial question. And finally, how does the evolution and the kinds of scaling relationships that one might derive for the melt time or dissolution time, how does that all depend on the initial shape? And this is going to review two papers, one of which was published earlier this year in the journal Fluid Mechanics, and the other is currently under review. So the question of whether a dissolving body converges to a universal shape was considered previously by Nacuzzi, Goldstein and Steinbock. And by conducting a series of lab experiments involving dissolving cylinders of candy, they conjectured that the tip formed a parabola. And we'll be considering that question later from a theoretical perspective. It's useful first to review the buoyancy-driven dynamics assuming a fixed body. So these equations here describe the dynamics of a boundary layer flow which is driven by buoyancy generated by dissolution along the boundary. And I've assumed here the case of dissolution, but a very similar set of equations applies to heating or cooling, and they represent the conservation of fluid mass, momentum and solute mass. And you can solve these subject to suitable boundary conditions, which are given down here, a no-slip condition and a Dirichlet condition on the maximum solute concentration occurring at the wall. So it's worthwhile first thinking about what happens in the case of a vertical wall. where alpha is pi over 2 everywhere. And in this case, there are similarity solutions. So if you do a scaling analysis, you find that the boundary layer grows as the distance along the wall S to the power quarter. And you can recast the system in terms of these similarity variables, and you get this ordinary differential system on the right here, where SC is the Schmidt number. And the quantity we're particularly interested in is the solutal flux at the wall, which we call Q. And from the similarity scaling, you can show that that decreases as the distance along the wall to the minus quarter. And there are lots of generalizations of this theory, which I've listed some at the bottom here. And interestingly, you very often preserve this self-similar structure with this scaling for Q, with the effect of all these complications just changing the prefactor. So the new thing that we consider is to allow the boundary to evolve in time. So we allow the boundary, which we call h, x of t, to depend on both space and time. And what we're going to do is to couple this boundary layer system at the top here to an evolution equation for h, which we have in the middle here. And that follows from conservation of solute mass along the interface, which says that the normal rate of recession v is proportional to the solute mass flux q. And the way to think of this is that if you know h at a given time, you can solve the system at the top there for c, and then you can plug that into the evolution equation and repeat the process. And from that interesting interaction between these equations, you'll get emerging shapes developing. And just a quick note that I've neglected here the time dependence in the boundary layer equations, despite the fact that the boundary is evolving forwards in time. And I'm going to talk about that in a minute. And this system here depends on 4 equations, which is quite complicated. And so it's interesting to think, can we simplify this somehow? It turns out that a significant simplification of the steady boundary layer equations is available if we assume that the Schmidt number is sufficiently large. So something greater than 1 is sufficient for this. And what happens in this limit is that the flow develops a solutal sublayer in which the inertial contribution to the momentum balance can be neglected, which is shown in the middle here. And you might be wondering, how does that help? And it turns out that there is a transformation available on neglect of that term, which transforms the system to the same similarity system that I showed you earlier, that applied to a vertical wall. And the similarity, this transformation, I haven't shown you it here, but it depends on sine of alpha to the third and things like that. The upshot at the end of the day is that you get a general formula for the solutal flux along any general shape, which is given at the bottom here. And this is really good because it allows us to develop a single PDE for the evolution of h. And so what I've done here is to take that expression on the last slide and substitute it into the evolution equation for h. And what we get is this expression on the right here, which gives a single PDE. And it's got 2 parts. So the numerator represents the contribution of local drive, which drives faster convection and therefore a faster recession speed. And the denominator has an integral, and what that's representing is the insulation effect of solute accumulation as you move down the body, which acts to insulate the boundary from the fresh ambient fluid. And the parameter A is a material parameter which will be dependent on the configuration that you're thinking about. Just before thinking about solutions to this model, I'm going to return to this question of the assumption of steadiness of the boundary layer equations. And what I've shown here are the general unsteady equations. And it turns out that the assumption of quasi-steadiness that we've assumed in the boundary layer model can be measured by this dimensionless number here, gamma, which is the recession speed divided by the characteristic flow rate of the convective flow. And if the recession speed is very slow, then the boundary layer can be assumed to be steady or quasi-steady. And the reason for that is, the way to think about that is that the boundary layer dynamics is constantly readjusting or resetting itself to conform to the new surface profile, effectively instantaneous. And that's because the convective flow is sufficiently fast. But what's really interesting about this dimensionless number is that it spans a limit in which you have this quasi-steady situation on the one hand, and you have an unsteady diffusive problem on the other. So if you have a situation where the convection is extremely slow, then diffusion takes over, or conduction takes over, and you end up with a classical Stefan problem. And so there is a spectrum which bridges that problem to our problem, and in the middle here, if gamma is order 1, then all the terms are relevant, including unsteady and convection. And the reason I really like this is because it shows how the introduction of convection into the system also introduces with it the steadiness of the fluid flow. Just to show some illustrative solutions of our model, the other thing you need to specify in the model is the initial condition. And so what I've shown here on the left are two different initial conditions. So we've got a wedge shape to start with, and then a rectangular shape. And what these solutions show are some very different phenomena. And so if you play the first one, there are various things to point out. So it descends with what appears to be a linear descent speed approximately in time. And the other thing to point out is that the initially sharp tip rounds out with time. And what I've shown on the right here is the position of the tip as a function of time. So this is the distance from the initial position. And what it shows is that it descends as a t to the 4/5 relationship. And that's true for every value of m. Although the different values of m have different prefactors in that descent law. If you play the movie with the rectangle, you find there are some interesting differences. So the first most striking difference is that this shape actually sharpens with time instead of blunts. And it actually sharpens for all times and gets extremely sharp at late times. It forms a needle-like shape. And you can see on the right here in the descent position, there's another interesting difference, which is that this situation undergoes a regime transition from a t to the 4/3 to a t to the 4 at late times. Before considering these solutions in more detail, it's useful to point out a general universal feature of all the solutions, which is that the tip always forms a parabola. And how can we work this out? If we try a general power law in the governing equation and take the limit x tends to 0, then we find that a parabola is the only shape for which the tip descends at a finite speed. So of course you can initialize the shape with a non-parabola, and in that case the shape would instantaneously adjust to being a parabola for all subsequent times. And so we can write a general expression for the tip shape in terms of a curvature or tip sharpness, which we call S. And if we take that expression and substitute it back into the governing equation, we deduce this interesting general law in the bottom right here, which relates the tip descent speed and the tip curvature S. And it shows that sharper tips descend faster. So this appears to address, theoretically, the question of the ultimate tip shape considered by Nikuzi, Goldstein and Steinbock. And you might be wondering what's special about a parabola. Well, it turns out that a parabola is the special shape for which a free convective boundary layer of the kind we're considering here predicts a locally smooth recession speed around the tip. A nice place to start with considering the evolving forms is the case of an initially wedge-shaped body. And the reason for that is that this is a special case that admits similarity solutions that apply for all times. And you can deduce that by doing a similarity scaling analysis of the governing equations and this initial condition. And what you find is that both the horizontal and vertical dimensions both scale as t to the 4/5. So if you transform the PDE in terms of these variables, you get this ODE at the bottom here, or integral differential equation. And we generally solve this using a shooting method. Different similarity solution for every value of m. And what this plot shows is the prefactor to the tip descent position, which we call f0, as a function of that parameter. And so this shows every single solution that's possible in this case. And we can see here that there is a spectrum of solutions which bridge shallow situations to steep situations. And what this reveals is that there are two different asymptotic regimes for dissolving or melting a body, one in which it's shallow and one where it's steep. And so in the shallow model, we get this asymptote, 1.49 m to the 2/5, and in the steep asymptote, we get this different asymptote, 1.30 m to the 4/5. So what's happening here is that there are two different reductions of the model that are possible. So for a shallow slope, you can neglect this dh by dx squared in the governing equation, and the resulting simplified governing equation has a universal solution subject to scaling, which I've shown on the right here. And similarly, you can neglect the 1 in the limit of a steep slope, and you get this fundamental tip structure that I've shown on the right here. And you can look at the asymptotics of these two situations, and in the shallow case, you have quite a simple connection between the parabola at the tip and the initial shape profile far downstream, which in this case is linear. But in the steep case, you get a more intricate double deck structure, and that's because the parabola is always shallow, and so the steep approximation breaks down some distance near the tip. And what actually happens is you get a much broader x to the 4/3 region, which is much more representative of the tip shape at a large scale, but it's still parabolic at the finest scale. And I'm going to hand over now to Megan, who's going to talk about comparing these theoretical predictions with lab experiments.
We decided to compare our theory to experiments using hard candy. Hard candy is made from sugar and corn syrup with a bit of water. You heat it up to 150 degrees, and when it sets, it forms a kind of hard substance. We placed candy cones in a tank of fresh water, backlit by LED tape. The cones are raised up on a stand so that the sugary water would have somewhere to collect. Here's a video of a typical experiment. We measured the parameter A from our experiments. So we examined the recession rate of the boundary in the horizontal direction, the radial direction, as a function of distance from the tip, h0 minus z. We then fitted a function of the form AC times distance from the tip to the power of a quarter. From AC, we can get the parameter A, which depends on just the material that we're using in the experiments. We found for the 4 experiments we did, we got similar values for A. So around 1.4 to 1.6 times 10 to the minus 4. First, we examined the collapse of tip positions. So the steep theory predicts that the motion of the tip should follow the form of a prefactor F0, which is predicted from the theory, multiplied by A times T to the power of 4/5. We use an analog axisymmetric theory, so it has a slightly different prefactor from the 2D theory. When we rescale our 4 experiments, we find that there is an excellent collapse. So here, notice that the F0 comes from the theory, the A we measured from experiments, so this involves no fitting of any of the parameters. We can also look at the full theoretical prediction of the shape and compare this to experiments. So here we can see when we rescale the horizontal and vertical axes, there's an excellent collapse. The blue line is the initial condition of the shape, the black dashed line is the prediction from the theory, and the theoretical shape matches well to the experimental shape.
Thank you, Megan. So far in the talk, we've primarily considered the case of initially wedge or cone-shaped bodies. But of course we can consider more general initial shapes, and actually the wedge or a cone is a very special case where there's an exact similarity solution for all time. So as another example, let's consider a nearly rectangular block-shaped initial body. And you can see the evolution here at a bunch of snapshots, and on the right here you can see this transition between a t to the 4/3 and a t to the 4, which I showed earlier. So what's happening here is the solution is transitioning between two different similarity solutions, and so one in which it's steep and the other in which it's shallow. And by suitably reducing the governing equation, we can actually derive generalized similarity solutions that apply for any given initial power law shape, where n is the initial power law exponent. And I've shown two examples of this, one for 0.5 and one for infinity, corresponding to an initially spiked or an initially rectangular body. And what's interesting is that these two similarity solutions predict different scalings. So for example, the height descends as t to the 4/3 in the shallow regime for n equals infinity, but it predicts h goes like t to the 4 in the steep regime, which agrees with the numerical predictions that I showed earlier. Now, a particularly interesting difference between the two is how they predict the sharpness of the tip. So in the shallow regime, it predicts that the sharpness grows as t to the 4 times n minus 2 over 3n plus 2. And what that implies is that if n is greater than 2, then the body will sharpen. But if n is less than 2, then it will blunt. But in the steep regime, there's a different critical value of 4/3. Which means that these two similarity solutions are predicting different evolutions of sharpness, which we'll return to in a second. So just to illustrate how these two different regimes arise in time for different values of n, I've shown here a parameter time regime diagram, and so this is the initial power law exponent along the x-axis and time along the y-axis, and what this shows is the situations for which the different similarity solutions apply. So green shows the steep regime and blue shows the shallow regime. And what happens is there's a critical value of n equals 1 where you switch from the steep regime applying at early times and the shallow regime applying at late times to the shallow regime applying at early times and the steep regime applying at late times. And in the special case n equals 1, neither of the regimes apply because there's that special set of similarity equations that apply in that case. So let's now try to address this interesting question of when a body will blunt or sharpen. And as we just discussed, there is a critical value of n at which the shallow regime will apply first and then the steep regime will apply second. But also, if you remember from 2 slides ago, there's also a difference between the prediction of whether sharpening or blunting occurs in these two regimes. And so on the right here, I've plotted the tip sharpening exponent predicted by these two theories. So blue shows the shallow case and green shows the steep case. And so if this exponent is less than 0, then that regime will predict blunting. And if it's greater than 0, then it predicts sharpening. And what this shows is there are 4 different regimes which are, or situations which are labeled A, B, C, and D. So in cases A and B, both of the exponents are negative, and so the body will blunt for all times. There's a difference between A and B in the order in which the two regimes apply. In case C, the body will initially blunt, but then it will sharpen at late times. So there's an interesting transition there for those intermediate cases. And in case D, the body will sharpen for all time. So what this is showing is that there is a possibility for a body to either blunt or sharpen. It's interesting because you may think that dissolution or melting is a smoothing process, but the tip is a unique location where sharpening is possible. And it's a bit like a close analogy is to the sharpening of a knife. So if you're able to remove material laterally faster than vertically, then you will cause sharpening. which I've illustrated down here. And this transition between these two behaviors is occurring across this diagram here. So to conclude, we've managed to answer many of the open questions which we posed earlier in the talk. In particular, we've developed this new PDE, which describes the evolution of the shape of a melting or dissolving body. And this generalizes classical theories of natural convection to allow for that evolution. And analysis of this PDE reveals similarity solutions and also transitions between similarity solutions, and shows that the shapes that arise depend permanently on the initial shape that you prescribe. And as part of our theoretical analysis, we revealed this dimensionless number, which is the recession speed divided by the convective flow rate, and this very neatly puts this problem on a spectrum that includes the classical time-dependent diffusive Stefan problem. Is there a fundamental tip shape? Yes, there is. The tip is always parabolic at the finest scale. However, 4/3 power can also be more representative in some cases and much broader, even though at a microscopic scale the tip will still be parabolic. Does the tip sharpen or blunt? An interesting conclusion is that either is possible, and that's despite the fact that everywhere else in the shape the effect of dissolution or melting is to smooth the profile. Thank you very much.